Nature designs the oak tree to do one thing perfectly: stand vertical and resist the wind. Its grain is a fortress of fibers, rigid as iron and stubborn as stone. Yet, to build a ship of the line capable of surviving an Atlantic gale, or a carriage that withstands the violent recoil of a cannon, we demand the impossible. We need this rigid material to curve. Here lies the deadly paradox of the 18th century shipyard. If you saw a curve into a beam, you sever the grain, creating a hidden weakness that will snap under the first heavy load. To build true strength, we cannot cut the wood. We must torture it. We have to drag these massive trunks into a world of scalding steam and brute leverage, forcing the biology of the forest to yield to the will of the engineer. It is a dangerous, violent alchemy where solid matter is made liquid, and the difference between a fleet that sails and a fleet that sinks is measured in mere minutes of heat. In the sprawling shipyards and carriage, works of the 18th century, the fundamental conflict is always the same: the stubborn linearity of nature against the curved necessities of human engineering. Whether framing the hull of a 74-gun ship of the line or crafting the rims of a heavy artillery carriage, the master right begins not with the saw, but with a critical assessment of the timber's soul. Standing amid stacks of seasoned English oak or imported Baltic fir, the air heavy with the scent of wet sawdust and pine resin, the craftsman runs a rough hand over the graying bark of a massive balk. He looks for the run of the grain, seeking compass timber, trees that naturally grew with a curve due to wind or hillside exposure. But these are becoming rare and ruinously expensive. The alternative is the brute force of engineering, taking a straight, defiant beam of heartwood and forcing it to yield. This is not merely carpentry, it is a battle of wills. The wood, composed of thousands of years of thousands, cellulose fibers locked together, is designed to resist wind and gravity, standing rigid against the world. To bend it cold is to invite fracture. The fibers on the outside of the curve will tear apart in tension, creating what the yard workers call shakes, or catastrophic splinters that ruin the piece instantly. The Wright knows that to manipulate this dense material, he must alter its internal state, changing the very nature of the wood from a solid, brittle bone into something pliable, almost living, without sacrificing the structural integrity that sailors and passengers will bet their lives on. The preparation for this transformation is a ritual of precision and heavy labor that dictates the rhythm of the entire yard. Apprentices, their hands already calloused and stained with tannin, drag the selected timbers toward the preparation area, using iron-shod levers and cant hooks to roll the massive logs. Before any heat is applied, the wood must be dressed to its near-final dimensions, a process that removes the sapwood, the softer living outer ring that rots easily, leaving only the dense, iron-hard heartwood. Adzes swing in a hypnotic rhythm, the sharp steel shaving off thick chips that pile up around the workman's leather boots. They must leave the timber slightly oversized to account for the compression that will occur on the inside of the bend, a calculation made by eye and experience rather than written formula. If the beam is too thick, it will refuse to bend or will buckle under the strain. If too thin, it loses the strength required to hold the ribs of a vessel against the crushing power of the Atlantic. The wood is inspected for knots, distinct whorls where branches once grew, which act as unpredictable weak points that can snap like gunshots when stressed. A single hidden rock pocket or a short grain section where the fibers run diagonally across the beam can doom the entire operation, wasting weeks of labor and valuable material. The tension in the yard is palpable. This is raw capital and strategic resource sitting on the trestles. And the master wright's reputation hangs on his ability to read the hidden flaws before the true violence of the process begins. As the sun climbs and the shadows of the rigging lengthen across the workshop floor, the focus shifts to the agent of change: moisture and heat. The Wrights understand, through generations of guild knowledge passed down in hushed tones and fierce reprimands, that wood is essentially a bundle of tubes bound by a natural glue. When cold, this glue is glass hard. When heated and saturated with moisture, it softens, allowing the fibers to slide past one another without breaking. This is the secret that separates the novice from the master. In previous centuries, men would char the wood over open fires, wetting it with mops, a risky and uneven method that often scorched the surface while leaving the core brittle. Now, in this enlightened age of mechanical curiosity, a new beast sits at the edge of the yard, the steam chest. It is a long, coffin-like box constructed of heavy planks, caulked tight with oakum and pitch to hold back the pressure, connected by copper piping to a brick-encased boiler. This apparatus represents the industrialization of the craft, a move away from the organic intuition of the fire pit to the regulated, terrifying consistency of enclosed steam. The timber is slid into this dark maw, the heavy door is clamped shut with iron dogs, and the waiting game begins. The wood is no longer just a material. It is a patient on the operating table, awaiting the infusion of energy that will temporarily suspend the laws of its own biology, preparing it for a metamorphosis that feels less like carpentry and more like alchemy. The engine of this transformation is the boiler, a copper or iron vessel sitting atop a brick furnace that demands constant, sweating vigilance. The stoker, often a man with skin leavened by soot and heat, feeds the firebox with offcuts of oak and pitch pine, regulating the draft to maintain a roaring, steady heat without melting the boiler plates. The water inside begins to roil, and soon the invisible force of steam travels through the piping, hissing as it seeks escape through the microscopic imperfections in the joinery. The steam chest itself, a long wooden trunk capable of holding planks up to 40 feet long, begins to groan and creak as the temperature rises. This is not the high-pressure steam of the distant future railways. It is a low-pressure, saturating fog, but it is dangerous nonetheless. If the pressure builds too high without release, the box could explode, sending shrapnel through the yard. If it is too low, the heat will not penetrate to the center of the great beams. The master Wright walks the length of the box, listening to the timber inside, placing a hand on the exterior to gauge the vibration. He is listening for the thump of the steam hammering against the wood, ensuring the circulation is even. The air around the chest becomes tropical, a dense, choking humidity that clings to the wool coats of the workers, smelling intensely of cooked lignin, a sweet, earthy, heavy scent that permeates the clothes and hair of everyone nearby. Inside the dark, pressurized chamber, the physics of the wood are being fundamentally rewritten. The steam, maintained at the boiling point of water, forces its way into the pores of the oak, condensing on the cooler surface of the timber and transferring its latent heat into the core. For every inch of thickness, the wood requires roughly 1 hour of steaming, a rule of thumb that is religious in its application. A 4-inch thick plank for a ship's hull demands 4 hours of relentless, unvarying heat. During this time, the natural cement holding the cellulose fibers together enters a plastic state. The wood expands, swelling tight against the confines of the box, becoming heavy and waterlogged. It is a passive time for the timber, but an active, anxious time for the crew. They prepare the bending floor, checking the heavy iron pins, the capstans, and the massive wooden molds or dogs that define the curve the wood must eventually match. Chains are laid out, greased with tallow to ensure they run smooth. Wedges are sharpened. The boiler stoker keeps the water level high, knowing that if the boiler runs dry, the copper will soften and collapse, resulting in a catastrophic blast. The sound of the yard, the hammers, the saws, the shouting, seems to fade into the background, dominated by the rhythmic chugging of the steam venting from the safety valve, a mechanical heartbeat counting down the moments until the extraction. As the allotted time draws to a close, the atmosphere shifts from maintenance to mobilization. The master signals the crew, a dozen strong men chosen for their back strength and ability to coordinate without hesitation. They wrap their hands in thick rags or don heavy leather mitts, for the wood they are about to touch will be scalding hot, effectively a solid block of boiling matter. The exit door of the steam chest is unbarred, the iron clamps knocked loose with sledgehammers. A plume of white vapor erupts into the cool air of the yard, blinding and instantaneous, swallowing the men nearest the opening. Through the mist, they peer into the tunnel, seeing the timber glistening, dark and slick with condensation. It looks different now, no longer the pale, dry gray of seasoned lumber, but a deep, rich brown, steaming violently as the moisture on its skin evaporates. This is the critical threshold. Once the wood leaves the sanctuary of the steam, it begins to cool immediately. The plasticity is fleeting. The glue will begin to set again within minutes. There is no time for discussion, no time for errors. The wood is pliable, yes, but it is also incredibly heavy, weighted down by the absorbed water, and it retains a lethal heat. The crew grabs the end of the beam with iron tongs and hooks, dragging the steaming leviathan out into the light, their movements synchronized by shouts, a human machine rushing to beat the inescapable cooling of the air. The moment the timber clears the steam chest, the yard transforms into a scene of controlled chaos. The beam, now flexible enough to whip like a sprung bow if mishandled, is rushed to the bending floor or the framing stage. Speed is the only currency that matters. The wood radiates a heat that scorches the air, causing the men to grimace as they shoulder the burden or drag it along rollers. It feels unnerving to the touch. Solid oak that yields slightly under pressure, resembling stiff leather or lead more than lumber. They slide one end of the massive plank into a fixed cleat or anchor point on the bending platform, locking it in place with iron wedges driven home by heavy mauls. This anchor is the pivot point for the entire operation. If it slips, the stored energy in the yaw. Bending wood will unleash itself, flinging men and tools across the shop like toys. The master right barks orders, directing the team to the free end of the timber. Here, the mechanical advantage is brought to bear. Ropes and chains connected to a windlass or capstan are lashed around the steaming tip. The men heave against the capstan bars, the ratchet clicking ominously as the slack is taken up, and the great beam begins to groan, a low tectonic sound of fibers sliding over fibers. The actual bending is a terrifying display of tension. As the capstan turns, pulling the timber against the curved mold or the ribs of the ship, the outer fibers of the wood are stretched to their limit, while the inner fibers are crushed into compression. The master watches the neutral axis, the center of the beam, making sure the strain is distributed evenly. To prevent the outer fibers from tearing apart in a jagged rupture, a flexible iron strap is often clamped along the outside of the bend, supporting the wood and forcing the compression inward. The wood screams, popping and cracking sounds that would signal disaster in cold timber, but here are merely the sounds of the structure settling into its new geometry. The men sweating at the winches must maintain a steady, relentless momentum. Stopping now would allow the wood to cool in a half-bent shape, ruining it forever. They are fighting the memory of the tree, forcing it to forget its vertical growth and accept the unnatural curve of the vessel's hull. The heat coming off the wood is intense, mixing with the sweat of the laborers, the smell of hot iron, and the sharp tang of stress-released oak tannins. It is a visceral, dangerous dance. A snap chain or a slip dog could crush a limb instantly. The wood fights back, pushing against the restraints with thousands of pounds of force, alive with the stored energy of the steam. Finally, the timber is pulled fully against the mold, the curve achieved. But the work is not finished. The shape is volatile, held only by the heat and the chains. Immediately, the crew swarms the bent beam, driving in iron dogs, clamps, and spikes to pin it savagely to the frame or the floor. Every inch gained must be locked down. They use heavy beetles, large wooden mallets, to strike the wood, shocking the fibers and helping them settle into their new positions. The iron strap is kept tight. Now the cooling phase begins, but it cannot be passive. If the wood cools unevenly, it will twist or cup. Sometimes the Wrights will douse the timber with cold water to freeze the outer fibers, locking the shape in place, sending clouds of steam hissing up to the rafters. The tension in the room slowly dissipates as the clamps hold, and the wood stops protesting. What lies before them is a triumph of 18th century engineering. A solid, continuous grain curve, vastly stronger than any cut shape, capable of withstanding the pounding of waves or the recoil of cannons. The timber, once a straight pillar of the forest, has been tortured, heated, and coerced into a tool of travel and war, its very internal structure rearranged by the clever application of vapor and leverage. The men step back, chests heaving, waiting for the master's nod, before turning back to the steam chest, where the next victim of their craft is already softening in the dark. The violence of the bending floor gives way to a period of anxious stasis, a phase the Wrights call setting the memory. Although the timber is now clamped into its desired arc, the battle is far from won. The wood possesses a stubborn elasticity, a desire to return to the straight geometry of its growth. This phenomenon, known as springback, is the bane of the shipwright's existence. As the heat bleeds out of the core and the moisture evaporates, the natural glue of the lignin begins to harden once more, locking the fibers into their new alignment. However, if the clamps are released too early, even by an hour, the beam will sluggishly uncoil, losing the precise radius required for the hull or wheel rim. To counteract this, the curve is often overbent, slightly past the required angle, a gambler's calculation that anticipates the inevitable slight relaxation of the wood once the iron dogs are removed. The drying process cannot be rushed with artificial heat, which would cause the exterior to check and crack while the interior remains damp. It must air dry, often for days, amidst the sawdust and noise of the yard. During this time, the timber is vulnerable, held hostage by the iron bands, groaning occasionally as it shrinks and settles, a sound that makes every carpenter pause and listen, fearing the sharp crack of a stress fracture that would render the massive piece into nothing but expensive firewood. Once the master judges the timber sufficiently set, cool to the touch and dry on the surface, the process of permanent fastening begins, often while the heavy iron clamps are still in place. This is the integration of the bent component into the greater skeleton of the ship or machine. Teams of borers advance with long-handled augers, pressing the spoon-shaped bits against the darkened oak. They turn the handles in a grueling, repetitive rhythm, drilling deep holes through the bent rib and into the keel or frame below. The air fills with the smell of friction-scorched wood as the steel bites in. Into these holes, they do not drive iron bolts, which would rust and rot the timber from the inside, but rather tree nails or trunnels. Long, dry dowels of locust or oak, slightly thicker than the holes themselves. Driven in with heavy mauls, the dry trunnels absorb the residual moisture from the surrounding steam timber and expand, creating a joint tighter and stronger than any metal nail. The sound of the yard is dominated by the hollow thud-thud-thud of these wooden pins being hammered home, locking the bent tensions of the structure into a permanent embrace that will last for decades. Yet, this stage is also the final tribunal for the material. As the wood dries and shrinks, hidden flaws often reveal themselves. A shake or longitudinal crack that was invisible in the green timber or disguised by the swelling of the steam may suddenly yawn open as the fibers contract. The master wright inspects the curve with a critical eye, looking for compression creases on the inside of the bend, wrinkles in the wood grain that indicate the fibers have crushed and collapsed rather than sliding smoothly. If these creases are deep, the structural integrity is compromised. The beam is condemned. There is a profound heaviness in the yard when a massive timber, after days of shaping, steaming, and bending, is marked with the chalk cross of rejection. It is dragged away to the scrap pile to be cut for blocks or fuel, a testament to the unforgiving nature of the material. But for the pieces that survive, smooth, taut, and perfectly arched, they have transcended their origin. They are no longer parts of a tree, they are now structural members, possessing a stored tension that gives the vessel a living rigidity, ready to face forces far greater than the wind that once swayed them in the forest. With the clamps removed and the shape permanently locked by the trunnels, the surface of the bent wood must be dressed for its final service. The steaming process raises the grain, leaving the wood fuzzy and rough, coated in a residue of tannins and iron stains from the tools. Carpenters descend upon the curved beams with adzes and curved sole planes, shaving away the outer layer to reveal the smooth, dense heartwood beneath. This dubbing process is delicate. They must follow the sweep of the new curve without gouging the stressed fibers. The visual result is striking. Unlike a saw-cut curve, where the grain lines run out continuously across the face of the wood, creating short grain weak points that can snap like a carrot, the grain of the steam-bent timber follows the shape of the arch perfectly. It is continuous, flowing like a river of fiber from one end to the other. This is the supreme advantage of the entire arduous process. A saw-cut knee or rib relies only on the sheer strength of the wood's cross-section, but a bent rib relies on the tensile strength of the entire log. It is an act of biomimicry, treating the dead lumber as if it were a living muscle, retaining its longitudinal integrity even in its new unnatural shape. The true value of this labor is only realized far from the safety of the workshop, in the violent reality of the open ocean or the rutted battlefield. When a ship of the line drives its bow into a 30-foot Atlantic roller, the hull shudders with a force that would shatter rigid masonry. A vessel built with short grain, cut timbers would be prone to catastrophic structural failure, its ribs snapping under the hydrostatic pressure. But the steam-bent frame behaves differently. It is a spring. It absorbs the shock, flexing microscopically and distributing the load along the entire length of the continuous grain, before rebounding instantly. The energy of the wave is dissipated through the very tension that was inducted in the steam chest. Similarly, the rim of a cannon carriage wheel, formed from bent ash or elm, survives the brutal recoil of firing, not because it is unyielding, but because the bent fibers hold together under impact where a joined or cut wheel would fragment. The steam engineer has essentially stored potential energy within the wood, creating a kinetic battery that pushes back against the crushing forces of the world, protecting the lives of the sailors and soldiers who trust in the invisible geometry of the hull. Finally, the bent timbers disappear from view, covered by planking, coated in hot pitch, or buried under layers of lead paint. The sweat of the bending crew, the roar of the boiler, and the sweet, choking smell of the steam chest are sealed away in the dark, airless spaces between the bulkheads. To the casual observer or the wealthy merchant inspecting the finished ship, the graceful curves of the hull seem like an aesthetic choice, a pleasing line drawn by a designer. They do not see the brute force required to conquer the straightness of the oak. Yet the longevity of the ship is the silent testimony to their craft. While lesser vessels hog and sag, their backs broken by the sea after a decade, the ship with the steam-bent spine sails on for 40, 50 years, its frame as resilient as the day it was pulled smoking from the box. The process ends not with a fanfare, but with the quiet satisfaction of the master wright, watching the vessel slip into the water, knowing that the forest has been bent but not broken, and that the marriage of fire, water, and wood has created a leviathan capable of conquering the globe. The masters of the yard knew that true strength lies not on the surface, but deep within the grain, forged by patience and pressure. We are building a library of these forgotten techniques, preserving the legacy of hands that built the world. Help us keep this knowledge from fading into the mist. Strike the subscribe button, share this craft with a fellow historian, and tell us in the comments, what other lost trades deserve to be pulled from the fire?